Welcome to MEI Mechanics. We're on the topic of dimensional analysis, and this is video 1.3, determining indices in a proposed formula. So just another reminder that in mechanics we only have three fundamental dimensions, which are mass, length and time. So any quantity in any formula that we are dealing with, we can write everything in terms of these basic dimensions. So this can be a very powerful technique as well in terms of finding a formula which is consistent with what we already know. So suppose that we have a possible formula for the speed of a wave on the surface of deep water. So this is a proposal that the speed of this wave, v, is a dimensionless constant times the density of the water to some power times the acceleration due to gravity, g, to some other power, and the wavelength of the wave, lambda, to another power. Is there enough information just within there to determine what these powers need to be in such a formula? Well, this is where dimensional analysis can come in. So let's have a look at what we have at this point. On the left hand side we have a speed that has dimensions L t to the minus 1, as we've previously seen. Density, we talked about that in video 1.1. Remember, it's a mass per unit volume, so it's mL to the minus 3. Acceleration due to gravity, well, that's acceleration, so it's L t to the minus 2, like meters per second squared. And lambda, we were told, was the length of the wave, the wavelength of the wave. So that's the length, clearly. So when we combine this with the formula, on the left hand side we've got something with dimensions Lt to the minus 1. K is dimensionless, so that doesn't come into this dimensional analysis. Then ml to the minus 3, that's the volume, the density, I should say, to the power of alpha. Then we've got a acceleration to the power of beta, and a length to the power of gamma. Now, if we deal with these brackets, we find that this becomes m to the alpha L. So this is it has a minus 3 alpha there, so minus 3 alpha, and then we also have L to the beta, so it'll be a plus beta, and an L to the gamma, so a plus gamma. Applying rules of indices here. And then T only appears in this one, so minus 2, and then to a power of beta, so it's to the power of minus 2 beta. So if we compare the powers on the left hand side and the right hand side, we see that for for m, there's no m on this on this side, so that means that alpha must equal 0. For L, on this side it's effectively a power of 1, so that means that minus 3 alpha plus beta plus gamma equals 1, and for T, that's just minus 2 beta, so minus 2 beta equals minus 1. Alright, so if we start with this one, this one's done for, so we've got alpha equals 0. This one is quite easy to deal with as well. That tells us that beta is equal to, well, we've got minus 1 and a minus 2, so that means beta is plus half. And then if we look at this one, then, well, alpha is 0, beta is a half, so that one is telling us that a half plus gamma equals 1. Therefore, gamma is equal to a half. So putting all that together then, our formula is going to be V equals K, then density at the power of alpha. Well, alpha we've said is 0, so that means the density is not actually going to appear in the formula. G to the beta, well that's g to the power of a half. And then gamma, lambda to the power of gamma, which is half. Or another way of writing that then would just be k square root of g lambda. So that concludes video 1.3, determining indices in the proposed formula. The final video in this topic, video 1.4, is modelling using dimensional analysis.